So it's the limit as xy tends to 3, 3 of an expression x squared y cubed take away x cubed y squared over x squared take away y squared. Okay. Well, one technique, and it's one I'm going to use here, is called factor and cancel. So you factor as much as you can. The bottom is the difference of two squares. So that's going to be x plus y, x minus y. This top term, I can pull out an x squared, y squared as a common factor. And that leaves me with a y take away x. So be comfortable with that. Yeah, got notes. Now, you are allowed to cancel y minus x with x minus y. That is allowed. But what is left behind is not just one. What is left behind?
-1.
-1. So basically just makes your answer negative. Right? So what I'm now have is the limit as xy becomes 3, 3 of negative x squared y squared over x add y. And at this point, I can replace the x and the y with 3. So it's negative 3 squared times another 3 squared over a 3 plus 3. And that's 9 and 9, so that's 81. And 81 over 6 can be reduced to 3. And there's our answer. That question, if I did one like that, would be in the multiple choice. It's really, short and sweet, isn't it? A couple of lines, boom, you're done. And it gives me a chance to put in, well, I'll show you what that might look like. The right answer, let's say I decided it was going to be C. I would then put in a 27 over 3 for those people who forgot about the -1 thing. Right, that's why that one would be. B, what would I do with B? What kind of mistakes would people make? Well, some people do some really weird algebra. Do not do this. This is wrong, always wrong, and always will be wrong. But some people cancel that one with that one and that one with that one, and they leave y cubed minus x cubed, which gets them a big fat 0. And some people think that you get a 0 divided by a 0, and the answer is infinity. So do you see in that question, there is one right answer, but each one of those wrong answers could happen if you made a wrong assumption or you did wrong algebra.
Yep.
So the moral of that story is be very careful when you do multiple choice. Just because the answer you got is one of the guys that's here, you tend to be, oh, I must have got it right because I've got 0 and they have 0, right? And couldn't it be I made the mistake and he figured it out? Now, it's easier if your answer is none of those 4 because you know you're wrong, in which case you go back and you figure out what number it is, right? But the chances are that is if you've made a common mistake, it will be one of these wrong guys. And so just be careful. That's all I'm saying. More points are lost in multiple choice typically as a percentage than are lost in section 2. That's my experience. I mean, if you look at your midterm, most of you are probably going to say, I lost more in my multiple choice than I did, whatever. I only got 70% in my multiple choice, got 80% in the section 2 stuff, that kind of thing. Okay, next question. Oh, I'm assuming. Is that okay, Dylan? Is that what you wanted to know?
That's perfect. Thank you.
Okay, who's next?
Number 24 on 14.3.
Let's find that guy. View, question 24. Question 24. Oh, God in Himmel. All right, so we have a function, a multivariate function, and looks like 3 variables, and it's e to the x, y, and then a weird z to the 7. And we're being asked to find basically that, right? So it's in order 1, 2, 3, right? According to Clairaut, couldn't I do that in any order I wanted? I could do the Z first, then the Y and the X. As I look at this, I don't think there's any advantage. I think every permutation is equally ugly, right? And so I might as well just do it in the order they say. So I'll do the partial derivative with respect to X. And this is a chain rule. It's an e to a something. So you go e to that something times the derivative of this power with respect to X. So that's a bit like saying X times some numbers. And so the derivative you get is that guy. So far, so good?
Yep.
Now, I'm just going to rewrite this fella a little bit differently. Now, the second one is differentiate this with respect to y. But this guy contains a y, and so does this guy. So what I'm going to do here is a product rule. A partial derivative version of it, but it's still the product rule. So if you differentiate this guy with respect to y, you get z to the 7. And then you leave this guy alone, plus leave this guy alone. And then you differentiate this with respect to z. And so you're going to go e to the x, y, z to the 7, followed by the derivative of x, y, z to the 7 with respect to z, which is going to get me 7 x, y, z to the 6. And so now I have that ugly guy.
That was to the y, not to the z.
Yeah. I apologize. Is there a fix for that? I'll just rewrite it down here. Right. So leave this guy alone. That part was fine. Differentiate, at least the first part was okay. But with respect to y, you're going to get an x set to the 7. Right. I think I'm thinking of the next line. So we have this fella. I'd probably combine these. And we're now ready for the last one. I think I'll do it up here. I'll need the room. That first one we did would have been a multiple choice question. And this one here would have been in a section 2. Right, you can see how much work's involved in it. So it's got more work. It's going to be in section 2. So to differentiate this guy, I guess I should put the original one up here. We have a z to the 7, e to an ugly power, plus an x, y, z to the 4, e to the same ugly power. So when you differentiate this expression with respect to z, you're going to have product rule and a different product rule. It's going to be f dash g plus f of g dash using these two guys. Then it's going to be an f dash g plus f of g dash using those two guys. Whoa, differentiate this term with respect to z. Leave the other term alone. Plus leave the first one alone and differentiate this guy with respect to z. So you get e to the xy z to 7 times the derivative of that. It's that one. Plus, I'm going to do this one underneath. If you differentiate this with respect to z, you're going to get 4y or 4xy z cubed. You leave this guy alone. Plus, you leave the first term alone. And then you differentiate this guy, and you get e to the x, y, z to the 7 times the derivative of this with respect to z again, which gets you another one of those guys. What do I have? I have this fella, this guy, and this guy is a common factor. So all those terms have that in it. Then I'm going to have 7z to the 6 plus, combine these, you're going to get 7x, y, z to the 13. This is going to get you 4x, y, z cubed. And that's going to get you 7x squared, y squared, z to the 10. And there's nothing even vaguely pretty about that answer.
What? At the top of the paper where you have f of x, y, where did you get the plus, or the second f, the plus x, y, z to the fourth?
Came from here. It came from the second part of this product rule. It came from fg dashed. See, this is f and this is g. So f dash g gave me this piece.
Oh, okay, it's
fg
14,
dash
not
gave
4.
me that piece.
Okay, that's what it is.
Okay. I'm a little bit disappointed because WebAssign could have made the question or tweaked it so that all of these kind of combined or at least cancelled, and you got, it's really cool when the answer ends up looking like this. I know this one didn't, but isn't it really cool when everything kills off and there's a little bit left over and it's quite nice looking? But this one, it's just
Shouldn't z be to
Mr.
the
Robertson,
yes.
you wrote when you rewrote the second derivative, you wrote x, y, z to the 4th, and that was previously to the 14th.
Okay, I'm not changing it now.
But yeah, but when you do the working, they do combine.
They do?
Answer.
Oh, okay.
How
A
do
lot
they?
or just a little bit?
Just a little bit. Just the
Okay.
4 xyz cubed is 14 xyz to the 13, and then that couples up with the 7, and then, so it's just one term difference.
Okay, that'll probably be a little bit different. So that you get 3 terms instead of 4 because if I picked up right, these two combine to give you 11x, y, z to 13. Right. Moral of that story, as you know, how careless it is when you, especially if you're rushing through things as I am. But if you were doing this in section 2, wasn't the only mistake I did a transfer of a number. I wrote a 4 instead of a 14. Now, in the big scheme of things, would you agree that it's just careless? It's not fundamental to the process. So I get 90% of the points, so would you? Unfortunately, if this was a multiple choice question, I know it probably wouldn't be, but if it had been, don't I very often have an E, some other answer? I would have picked E, some other answer, and I would have been wrong. Do you see how cruel multiple choice can be to you? So back to my be careful. But the process I did was correct, which is in a way more important. Right. God, time's shooting by. We're already 20 minutes and feels like I haven't done anything yet. What's next?
Could you do 1110 number 13?
1110 number 13. Oh, it's a way back. That's fine. Nothing wrong with that. It's in Maclaurin Taylor series section. And it looks like it was right at the end, almost the last question. And so we're being asked to find a Taylor series for a function called e to the 2x, centered at a equals 4. And essentially, they gave us that bit, and it's our job to fill that blank. Okay, so Taylor series, this definitely would be a section 2 question because the amount of work. So, oops, let's start over here. Here is the original function. The value of the function at 4 is e to the power of 8. If you find the derivative, the first derivative, you'll get 2 e to the 2x, and f dashed of 4 ends up being 2 e to the power of 8. You then do the second derivative, and don't call this guy 4. It's much better when you're doing this question to write down what the calculation is. So if you were going to differentiate 2e to the 2x, you'd go 2e to the 2x times another 2, but call it 2 squared. And when you do the value of the function at 4, don't call it 4, call it 2 squared e to the 8. And the reason why it's a good idea to leave things as calculations is you're looking for patterns. I think I already know this pattern, but I'm just going to do one more. The third derivative ends up being 2 cubed e to the 2x, and the third derivative at 4 ends up being 2 cubed e to the 8. Now, if you've done it correctly, you should be able to find the third, or not the third, the nth derivative at 4. So, first derivative, second derivative, third derivative. What would the nth derivative be based on patterns?
Two to the n times e to the 2x?
Not even 2x, just e to the 8. Right, can you see it? First derivative, it's 2. Second derivative, it's 2 squared. Third derivative, it's 2 cubed. Nth derivative, 2 to the n. What else is there? Well, e to the 8 is a fixed number, so it's not going to change no matter what derivative you do, so it's still e to the 8. Now, that's the guy that fits up here. Well, part of it, it's the nth derivative at a, x minus a to the power of n, all over n factorial. So the nth derivative at a is that guy. X take away a to the n is that guy, all over n factorial. So that's the entire package. We only really need to find this piece because they two are the same all the time, right? There's always an x minus a to the n in a Taylor's, and there's always an n factorial in the bottom. Our job is just to figure out what the nth derivative at a is, which is what we just did here, because a is 4. Did that help? Right. Do you want to see the radius of convergence thing, or are you okay with those?
Sure.
Okay. Now, it's not uncommon to find the radius, and later on sometimes the interval of convergence, but let's do the radius of convergence. You find that by the ratio test, which means that guy. And in this case, it's going to be the limit as n tends to infinity. One of the shortcuts to this is write this guy with all the n's replaced by n plus 1. And then instead of dividing by that guy, just turn them upside down. In other words, everybody in the top goes in the bottom, and everybody in the bottom goes to the top, but in terms of n. So I should be able to do a fair amount of cancelling. Let's see what we can do. Won't that e to the 8 kill off that e to the 8? Now, this 2 to the power of n will cancel 2 to the power of n plus 1. But what will be left? When a 2 to the n plus 1 cancels out a 2 to the n in the bottom, what's left? And does it belong on the top or is it in the bottom?
Would it be n plus 1 on the bottom?
No, look again. Right. There, that's me just isolating it.
Wouldn't that just be 2 on the top?
Yes. So just rotate it. Yeah.
N plus 1.
Right. Yep. Now, if you do an x minus 4 to the n plus 1 and you cancel it out with an x minus 4 to the n, are we all happy that there's an x minus 4 left, but it's on the top? Factorials, I'll just write this separately. You got an n factorial on the top cancelling with an n plus 1 factorial in the bottom, right? They do cancel. What's left and does it go in the top or the bottom?
It would be the n plus 1 on the bottom.
Okay. Are you all comfortable about the bits that are left over here in this question? Right. Now what you're going to do is, depends on what you've got, how this turns out, but this one turns out really nicely. In this case here, there's only one place that has an n, because these things here are really just numbers, right? We treat these as constants right now. So aren't you basically, if you do brute force, going to get 2x minus 4 over infinity plus 1, which I'm just going to call infinity. And so isn't the answer going to be 0? Right. Now, things get a little bit messy. It's much nicer when that's a number, right? So if this was 5, wouldn't the radius of convergence be 5? Right. If it was 20, the radius of convergence would be 20, right? You do a bit of tweaking, but that's what you would get. Now, this is 0. Now, according to the ratio test, don't things converge when they're less than 1? And since this answer is always going to be 0, regardless of what x is, right? It's always going to end up 0. Doesn't this mean that this always converges? So these are one of the 2 special cases. What is the radius of convergence if the series always converges, as it does here?
Infinite.
It's infinite. And what would the interval of convergence be if the radius of convergence is infinite? In other words, if it always converges, what is the interval of convergence?
Would it be negative infinity to infinity?
Right. So you see, that one finished quite nicely, right? Infinities are good. Now, there is another possibility, a totally different question. Imagine we had another one and we did blah, blah, blah. And the answer we got was infinity, right? We don't like infinity. Infinity is bad news, isn't it? What will the radius of convergence be when basically the series never converges except for one exception, right? What is the radius of convergence?
0.
It's 0. Now, the interval of convergence isn't an empty set. It actually does contain one value, and that's whatever A happens to be, right? So in our story, I think it was 4, right? So if that had happened to us, the interval of convergence would be the single digit 4, because when x is 4, won't this be nothing? And a whole load of nothings added up do converge. But it's almost like a trivial situation, isn't it? You know, you've got a power series, but it only works if the answer is 0. It's probably not a very effective power series, right? You can't do anything with it. You can't use it for anything because it doesn't work for anybody else except for one number, and the answer is going to be 0 when it's a number, which is kind of defeats the purpose. Kira.
Yeah, I just had a quick question just about notation. When it's the single value like 4, you use the squirrely brackets. I don't know what to
I
call
call them
them.
curly brackets. That's
Yeah.
probably not the right name, but I call them curly brackets. Yes.
I call them squirrely brackets. I don't know. It makes me
That
happy.
works.
So you use that because it's not an interval, so you don't need parentheses and you don't need square brackets. It's
Yeah.
just a set in notation instead.
Because we use the curly brackets when we want to write down terms of a sequence. So that would just be a sequence with one number in it, right?
Okay.
So it qualifies. That's what that notation means. Oh, since I'm on this one, pretend it was a different answer, and we got the fact that x minus 4, right? Let's say it was less than 2, right? That could happen. If that happened, the radius of convergence is 2. But how do we find the interval of convergence? So that's a little bit messier. It's easier when you've got that guy, right? Because the interval of convergence is basically all the numbers from -2 to 2. But when it's this guy, you have to do a little bit more work. You start off by converting the absolute inequality into what I call a sandwich inequality. What would you do to get x in the middle? Because you need x in the middle. What would you
Add
do
4
here?
to both sides.
Okay, and in this case you get 2, in that case you get 6. So your interval of convergence would be 2 to 6, right? Any value of x between 2 to 6 would work. And I wish I could say that's the end of the line, but a lot of people forget that when you do an interval of convergence, don't you have to test the 2 endpoints? And what that means is you have to check what x equals 2 is like and what x equals 6 is like. So you do it to one and then you do it to the other. And it is possible that that one might converge, right? It might converge because it's a p series or something, right? Or an alternating series, right? But whatever it is, it converges. But that doesn't mean that everybody converges. Couldn't the other one diverge, right? Right, one of them's an alternating series and it makes it, and the other is, 1 over n and it doesn't make it. So when that happens, you put a square bracket on this side and a curved on the other, and that is the final interval of convergence. So it's easy when the answer is infinite, right? And 0, right? The interval of convergence is, you can write it down. But when the R value is a physical number, then the interval can be quite messy and you're not even finished until you've tested the 2 endpoints. And so, that is definitely a section 2 question, right? Too much work to be a multiple choice.
Does it have to be the ratio test? Like always?
There's probably an exception to it. I could imagine occasionally you could use maybe an nth root test. Right.
Okay.
I can imagine that, but nah. The ones you're going to see are going to be ratio tests. That's probably the easiest way to say it.
Got it.
Right, what's next?
Could you go over direct comparison tests?
Right. Okay.
Kind of like when we use them, and briefly explain like what they are again.
There are 2 tests that have the word comparison test in them, right? One's the direct comparison, the other is the limit comparison test. Right. You should only use the direct comparison test. This is the safety one. Only use that if you have, for want of a better word, ugly terms. What does ugly terms look like? Ugly terms is if there's a sine squared n, if there's an e to the 1 over n, if there's an inverse tan of n, and situations like that. That is really when I would say you should use the direct comparison test. The limit comparison test is typically used when you have fractions made up of powers, right? So polynomial over polynomial limit comparison test is your go-to guy, right? If there's a sine squared or an e to the 1 over n or a cosine n or a tan or something weird going on, then you need to use a direct comparison test. So let's show you how that would work. Suppose someone went and said, I would like to find out, does that series converge? And I want to do it using, as I should, the direct comparison test. Can you see why I need to use it? There's this weird guy. So if it has a weird guy in it, use the direct comparison test. Kind of hard to describe what weird guy is, but you kind of get the gist of it. And so what you do here is you do a comparison. And would you agree that this guy is less than 1 over n squared? Now, why is that? Well, isn't the sine function less than 1, or at least when you square it, it's less than 1 to 0, right? Essentially. So you can state that as a kind of obvious, intuitive thing, right? You don't need to go into any clever math and try and prove it, right? You just state it. But of course, this guy is a p-series, isn't it? Because the comparison is that you need to compare this guy to somebody that you know. And isn't this a p-series? And isn't this a p-series called p equals 2? Does that one converge? Does 1 over n squared converge, that page series?
I forget if it's like over, if it's greater than 1, if it diverges, or if it's...
Okay, well, here we go. If it's greater than 1, it converges. And if it's less than or equal to 1, it diverges. So you probably should write that down in your direct comparison test sheet card, right? And then I think the reason you got them mixed up is, isn't a geometric series test the actual opposite of that? If R is bigger than 1, it diverges, and if it's less than 1, it converges. Is that what was getting in your head, right? You get 2 tests that kind of merge, or at least they cross over as far as the rules go. Well, since this guy is less than that, and this converges, don't you just say then by the direct comparison test, that one converges?
My trick for the p-series test is I always just remember that the harmonic, the 1 over n, diverges, and then I just use that as like my baseline. Like,
anything
okay,
under it diverges,
that
anything above it converges.
diverges.
Gotcha. Yeah, that's a good way to remember it. Yeah. Find the one, you know, the borderline between the goods and the bads, right? The converges and the diverges. That's a good way of looking at it. While my brain is on that, here is a kind of scary one. Right, the first one is not scary. The reason this starts at 2 is you don't want the log of 1 because 1 is 0 and that causes all sorts of problems. So that's not a biggie. What test would you use on that guy? He looks like he's a direct comparison test because he has this ugly thing in it, right? And it is. If you try to use the limit comparison test, you end up with a limit equals 1. And a limit equals 1 means you don't know, right? That's what happens when you do that. So it's not a direct comparison test because you can't really compare that to a p-series. I mean, you might think you can, but the log n kind of wastes it, right? So what test would you use for 1 over n log n? You've got 9 to pick from. Who are you going to pick?
Would it be the integral test?
It would be.
Because a U sub with ln of n, right?
Yeah. And it, by the way, I believe it diverges, which you kind of probably thought it should, right? But that would be it. If I gave you that question, that one there, that one would almost certainly be a section 2, because you know the integral test is probably one of the longest tests that you possibly could use. And if you do get it, you would probably be told, use the integral test to find this, if it converges or diverges. So when I give you a question and I say use whatever the test is called on this guy, that is not that's not a recommendation or a suggestion. It's a do it that way. One, because I want to see, do you know how to do the integral test? And two, because it's probably the only test that you can use that will really work. So if you tried a ratio test, or you tried a comparison test, or one of the other many tests that we've got, it wouldn't work. You might end up telling me the truth in the sense, oh, it diverges, but you might be telling me it for all the wrong math, right? For instance, you might say, oh, I can do this one in my head. This guy is less than that, that diverges. Oops, so let's do it the way. This guy is greater than that, that diverges, so he must diverge. Well, by the way, that's not greater than that. That's actually less than that. So you'd be dead right on line 1. And you might think, I don't know why you can say that that's actually the truth. Well, let's put in a number. Isn't 3 times the log of 3 bigger than 3? Right? Isn't 1 over a bigger number smaller than 1 over something that's not as big? I mean, you can put it in your calculator. No matter what number you pick, won't this guy always be smaller than that? But in a comparison test, if you want to prove that you are a diverger, don't you have to prove that this is bigger than that? Right? You have to prove you're bigger than a diverger to be divergent, right? If you're smaller than something that diverges, that doesn't prove that you converge. It doesn't prove you diverge, right? It just means, well, nothing useful, right? There's no evidence either way when you do it that way. So that's a simple case. Now, I'm not saying I have, because actually, I have actually written the test. So I know it's in the test. So in and I'm about to say here is just general. I could give you questions, and I have in the past, where you're given 4 series, and I say which is the only one that converges and which is the only one that diverges, and I put it in multiple choice. You seen that question? I think we did one in midterm. That is totally valid. But in those questions, I do not expect you to do the integral test, the limit comparison test, and all the other stuff. I want you to just look at those guys, and your gut feeling should be which one works and which one doesn't, right? You should be able to just look at something even before you proved it. So I'll give you an example, and then we'll move on. I know that diverges. I don't need to do any test to prove it. I just know that that's going to diverge. Anybody want to tell me in their brain how they know that's a diverger?
Is it because we know the top is getting bigger faster than the bottom?
That'll do. Yeah. Right. I know that diverges, even although I'm not going to do the limit comparison test, which is what I need to do to prove it. And by the way, I'll do the divergence test on that one if I wanted to prove it, but I know that one diverges. How do I know it?
Kind of as if you did L'Hopital's thing. It would
Oh,
come
you'd
out
get
to-
that the limit would end up eventually being 0. Is that what you're thinking, Dylan?
Yeah, well, I know that you'd be left with an n to the 4 at the bottom. Well, but you'd be left with just one n on the bottom because it's larger.
Okay. And why does that make you know it's going to diverge?
Because like I was thinking p series 1 over
Yeah,
n.
okay, that'll work.
Yeah.
So would you agree that if you just ignore these terms, isn't that basically a 1 over n, which is essentially what Dylan was saying in a different way? Isn't that a 1 over n? So multiple choice, you do not do any tests, really. Shouldn't you, or at least vaguely do tests like, I'll cover it up with my finger and see what it kind of looks like, kind of test, but nothing formal. So don't spend tons of time writing multiple choice things down, right? Multiple choice is 3-minute rule, right? If it takes you longer than 3 minutes, you're doing it wrong. Any other questions now? Let's move on. Oh God, no, not moving on. It'll be a really quick one. Go.
Okay, it's just from the chapter 10 test that we did the other day. It was the one, forget which number it is, but it's with respect to x and y, and it's a question that has like y and an argument to the 4th power, and I couldn't get the y value.
Looking for some with a 4th power in it. Who knows where? Well, see, mine is changing.
Okay, it's like y, and then there's an argument in parentheses to a power.
Right, I'm going to go over to the thing, and this is starting at 1. You say stop or whatever, or tell me the number. There's 2. Here's
Wait,
3.
I can't see.
Oh, you can see. I haven't shared it. Sorry. Right, let's do it again. There's 1.
He's referring to number 10.
Okay, let's jump to 10. That one? Is that the one you're talking about, number 10?
Yes. Thank you.
Okay, right. Let's get this guy in the road. So it's a chain rule. I can tell that just looking at it. It's actually a product rule and a chain rule. So it's going to be x plus x squared y all to the 6th again. So let's get moving on this one. So if you want to do the partial derivative with respect to x, you're just going to treat that as a constant. So in this case, it's just a chain rule. So it's going to be multiplied by the power, reduce the power by 1, followed by the derivative of the inside function with respect to x. So that gets you 1, and that guy gets you plus 2xy. And then I'd probably just rearrange it a little bit to make it look pretty. Still points. And that's that one done. If you want to do the partial derivative with respect to y, however, you're going to realize that there's 2 different places that have a y. So this is a product rule. At least it starts off life as a product rule. And some chain rule stuff there. So you differentiate this guy with respect to y, you get 1, and you leave the other guy alone. Plus, you leave the first guy alone, and now you differentiate this with respect to y. So what's that going to give me? 6 x plus x squared y's to the power of 5 times the derivative of what's inside with respect to y, which gets me another x squared. So in this case, I have that guy plus 6x squared y, that guy, and then style points says I should pull out 5 of these fellas, and that leaves me 1 of these guys plus that guy. So I have, that's a y there. I have this guy, and if I've done it right, these 2 actually can combine. Now I have, what's that, 7 x squared y And then I notice that there's a common factor at x. So I'll pull an x out, and that'll leave me 1 plus 7xy, and then finish with the ugly figure. So that's what I get.